Okay, this video is going to talk about the main theorems within diagonalizability of linear operators and matrices. We won't show proofs, but we will look at and see what happens with theorems. Maybe with the exception of this very first theorem. We'll see sort of why that's true. Okay, so first off, a polynomial splits over a field if there are scalars, c a1 to an, such that the polynomial is equal to a constant plus the product of linear terms. So here's a nice example. What do we have here? 2t squared minus 6t. Factor out the 2, factor out the t, you get t minus 3, right? So constant, linear term, linear term. This is an interesting non-example. It doesn't split, I should say, over the reals, right? Because there's no way to factor that. But it actually does factor over the complex numbers. You can think about that on your own. Okay, so first big theorem, the characteristic polynomial of any diagonalizable operator splits. Okay, so think about that. What does that mean? Probably the biggest result here is actually the contrapositive of that, which is equivalent to the theorem. If you prove the theorem, you get the contrapositive. If the characteristic polynomial doesn't split, then the linear operator is not diagonalizable. We didn't really have a condition that you could say, no, there is no way to diagonalizable, no way to diagonalize. Not just I can't find it, but it really doesn't exist. So how would you get a cool result like that? Well, the proof idea is sort of as follows. Let's imagine that t is diagonalizable. Well, what does that mean? That means that you have this ordered basis of eigenvectors by theorem 5.1, right? And so then you get the matrix representation of t in terms of beta is, say, lambda 1 to lambda n, where those are, and these are all zeros, where those are the eigenvalues corresponding to these eigenvectors, right? But then think about the characteristic polynomial in this basis. Okay, if you think about the characteristic polynomial in this basis, f of t, right, it's the determinant of t beta minus t in, right? Well, what is that? I mean, this just has lambda 1 minus t all the way to lambda n minus t. These are all zeros, so the matrix of this, the determinant of this matrix is really like lambda 1 minus t. If you just took out n negative 1s, you'd have t minus lambda 1 all the way out to t minus lambda n. So you can sort of see that's pretty clearly splits. Okay, so splitting is necessary. If you don't have splitting, you don't have a diagonalizable matrix. But let's look at an example real quick here where we see that's not, this is supposed to have an arrow, where that's not enough, okay? So, sorry, we have a linear operator from degree 2 polynomials to degree 2 polynomials. So that is going to degree 2 polynomials with real coefficients, defined by the derivative, right? Let's let beta be the standard basis. Well, I imagine you can figure out what the matrix representation in terms of the standard basis is, right? So what happens to the first element of the standard basis, right? 1, well, the derivative is going to have 0 in all the coefficients. What happens to the second order of the standard basis? Well, it's going to have 1 in the constant term, no none of these, and none of these. And I'm expecting that you could work this out. What is the derivative of x squared? Well, it's 0 constants, 2 x's, and 0x squared terms. So there is the matrix representation of that linear operator in the standard basis. Well, what is the characteristic polynomial then? The characteristic polynomial is the determinant of this minus, right, so t beta minus t I3, right, that's, let's see, negative 0 minus t 1 0 0 minus t 2 0 0 minus t. That's an upper triangular matrix, right? So what is it? Negative t times negative t times negative t, which is negative t to the third. This is a splitting polynomial, right? I mean, so it's linear terms, t times t times t. That's a splitting polynomial. But it only has one eigenvalue. So that means therefore all eigenvectors must come from the null space of t minus lambda I3, right? They must have t of the vector equal to lambda of the vector. But what was lambda? Lambda was 0. So that's the null space of t, right? Well, what is the null space of the derivative operator? Well, that's exactly the polynomials that are constants, right? Such that a is any real number. That's exactly the subspace that's 0. So all the eigenvectors must be in there, therefore the eigenvectors have no possible way of spanning. They can not span this space. So it's necessary, but it's not sufficient. So let's see what else we can do here. I need two definitions to get us there. Given a polynomial, f of x, and c, a 0 of the polynomial, remember that the multiplicity of the 0 is the largest positive integer k, such that x minus c to the k is a factor. So remember in the last one, we had something like negative t squared. 0 is a we had negative t to the third. This is a multiplicity 3, 0, right? And if you had y equals 2x minus 1, x plus 2 squared, negative 2 would be a multiplicity 2, 0. Okay, and then we need another definition, an eigenspace. Let t be a linear operator on a vector space V, and let lambda be an eigenvalue of that linear operator. The eigenspace of t corresponding to lambda, which we denote E sub lambda, is the null space of t minus lambda identity map. You notice we looked at that in the last problem. So E sub lambda is the null space of this. In other words, it's the set of vectors such that t of x is equal to lambda times x. Right, and the eigenspace of a square matrix is just defined to be the corresponding eigenspace on the left multiplication by A. Okay, so why do we need multiplicity and eigenspace? Well, they are fundamentally linked. So let t be a linear operator on a finite dimensional vector space, and let lambda be an eigenvalue of t, having multiplicity m. The dimension of the eigenspace, well, it's got to be at least 1. You can't have an eigenvalue without having one eigenvector and all scalars of that. So the dimension has to be at least 1, but it can't be bigger than the multiplicity of the eigenspace. Okay, I'll leave the justification of that. You can read about it in the textbook. And it's even more than that. Okay, if T is a linear operator on a finite dimensional space such that the characteristic polynomial splits. Remember, if it does not split, the operator is not diagonalizable. But if it splits, and if you have k distinct eigenvalues, T is diagonalizable. That's what we're looking for. If and only if the multiplicity, right? So mult lambda I equals dimension of the eigenspace. This is the key characteristic. In fact, maybe what I should have written is 1, the characteristic polynomial splits, and 2, the multiplicity of each 0 of the characteristic polynomial is equal to the dimension of that eigenspace. If those two things hold, it is diagonalizable. And if either of those things fails to hold, it is not diagonalizable. So let's wrap up with one final example. I've got a matrix here. Let's see what we can do with that. What is the characteristic polynomial? F of t there, right? It's the determinant of a minus ti. Well, that's, let's see, 1 minus t, 1, 1, 0, 1 minus t, 0, 0, 1, 2 minus t. We'll take the determinant from the first column. So it's 1 minus t times the determinant of this minor. And this minor, it's just this diagonal, 1 minus t times 2 minus t times minus 0 times 1. So that's the characteristic polynomial. Notice it has an eigenvalue lambda equals 2 with multiplicity 1. That's taken care of. It automatically has that. But what about lambda equals 1? We need to know whether that has multiplicity 2. And if we can see that E lambda, dimension of E lambda, is 2, then you just pick a basis for this space, and that's your 2 eigenvectors to put with this eigenvector, and you have that diagonalizable basis. Okay, so what do we need there? That's really the nullity, right? The dimension of this is really the nullity of I minus A minus lambda I, right? Well, what is that? The nullity, I guess the easiest way to see that, the nullity is the dimension theorem. Remember, that's the overall space of the domain 3 minus the rank of A minus I. Well, let's A minus I, let me just remind us what that is. That's this matrix minus the identity matrix. So we're going to subtract 1 from the diagonals, right? So we get 1, 1, 0, 0, 0, 1. What's the rank of this? Well, you can see the middle row certainly isn't linearly independent from anything, and the top and the bottom row are the same. So the rank of this matrix is 1, 3 minus 1, so the dimension is 2, and so therefore A is diagonalizable.